Today we are going to discuss modern periodic table and modern periodic law. So mostly in 1911, when he was working with the spectra of 38 metals, he identified that the elements fit into better patterns when organized according to nuclear charge. The nuclear charge is related to number of protons in the nucleus. And the atomic number is the number of protons in the nucleus. So he identified when elements are arranged in the increasing order of their atomic number, a regular pattern is obtained. So he arranged elements in the increasing order of their atomic number, and that led to the modern periodic table. And his experiments led to modern definition of atomic number. And again, periodic table organized according to atomic number instead of atomic mass. So he developed a periodic law that is different from Mendeleev's periodic law. This periodic law is known as modern periodic law. Modern periodic law. What is modern periodic law or Moseley's periodic law? Modern periodic law states that the physical and chemical properties of the elements are periodic functions of their atomic number. The physical and chemical properties of the elements are periodic functions of their atomic number. That is modern periodic law or Moseley's periodic law. What is Mendeleev's periodic law? The physical and chemical properties of the elements are periodic functions of their atomic numbers. Atomic mass. But Moseley's periodic law or modern periodic law that states that the physical and chemical properties of the elements are periodic functions of their atomic numbers. So you have to by heart it. It is an important law. It is the basis of the modern periodic table. Now, in Moseley's periodic table, the elements are arranged in the increasing order of their atomic number in 7 horizontal rows called periods and 18 vertical columns called groups. So in modern periodic table also you can see periods and groups, but there is a difference in the number of groups as compared to Mendeleev's periodic table. In Mendeleev's periodic table, only 8 groups, but here 18 groups. But the number of periods are same, 7 periods are present. Now what is a group? Vertical column. What is a period? Horizontal row. Then how will you determine group of an element? If you know the atomic number, you can write the electronic configuration, and number of electrons present in the outermost shell determines the group. For example, sodium atomic number is 11. 1s2, 2s2, 2p6, 3s1. Outermost shell is 3. In the shell, 3 only 1 electron. So its group is 1. And the period is determined by number of shells present in an atom. So sodium has 3 shells, 3s1. So its period is 3. What is the reason for periodicity in properties of elements? It is an important question. What is the reason for periodicity in properties of the elements? The reason, what is periodicity? After definite intervals of atomic number, a recurrence of similar electronic configuration takes place. So, the properties are also repeating. After definite intervals of atomic number, a recurrence of similar electronic configuration. For example, sodium 3s1, outermost configuration is 3s1. After 8 elements at potassium, the configuration is 4s1. The electronic configuration is repeating, similar electronic configuration. Therefore, the properties are also repeating. Since the properties depend on valence electrons, elements with similar electronic configuration have similar properties. So what is the reason for periodicity in properties of elements? Similar electronic configuration after a certain interval of atomic number. That is the reason. The properties depend on electronic configuration. Okay, now you can see the modern periodic table. Here some of the elements are not named. 118 elements are discovered now. And here you can see 1, 2, 3, 4, 5, 18 groups. And how many periods? 1, 2, 3, 4, 5, 6, 7 periods. And here below the periodic table, you can see 2 rows of elements. They are known as lanthanides and actinides, or F-block elements. Here you can see lanthanides from lanthanum to lutetium. Actinides from actinium to lawrencium. Actually, lanthanum and actinium belongs to the D block, but their properties are very similar to that of F-block elements. Therefore, they are included here. Lanthanum and actinium. So it is modern periodic table. Now, I think you are familiar with this modern periodic table. You are studying it from the lower classes, the modern periodic table. Try to study the names of the elements and the symbols. Okay, the modern periodic table. Here you can see UUT. What is this UUT? UUP, UUS, UUO. What is it? 113 UUT, 115 UUP, 117 UUS, 180 UUO. What is it? Or how these symbols are given to these elements? So there are certain rules to name an element immediately after its discovery. Before giving a permanent name to the element, we will give a temporary name to the element based on its atomic number. That we can see. How can you name a newly discovered element? Elements after 100. Before that, you just see what are the advantages of long form of periodic table. What are the advantages of long form of periodic table? First one, it relates position of an element to its electronic configuration. So the properties are directly depending on the electronic configuration. And when you arrange the elements in the increasing order of their atomic numbers, the arrangement is in the order of electronic configuration. So from the electronic configuration, we can clearly say which is the group of the element and which is the period of the element. Already we discussed the case of sodium. 3s1 is the outermost electronic configuration, so we can say it belongs to first group, and 3 is the outermost shell, so we can say it belongs to third period. So this periodic table relates position of an element to its electronic configuration. Second one, a logical classification of groups. Elements in the same group have similar outer electronic configuration. A good logical classification. We cannot see it in any other classifications. If you analyze a group, they have a general electronic configuration. For first group, NS1. For second group, NS2. For 18th group, NS2NB, NS2NB6, a general electronic configuration. You can see a general electronic configuration. So that is the advantage of this long form of periodic table. Based on their electronic configuration, elements have been grouped into S, P, D, and F blocks. The periodic table mainly classified into 4 blocks based on their electronic configuration. So we can study all the elements in 4 groups. That is an advantage of this periodic table. A satisfactory position is given to elements of group 3 to 12. A satisfactory position is given to elements of group 3 to 12. These are the advantages of modern periodic table. What are the defects of long form of periodic table? Again, position of hydrogen is not settled, though it has been placed along with alkali metals. It is not belonging to alkali metals. It has given a position above alkali metals. But it has no similarity with alkali metals. Some similarities are there, but a lot of difference. That is one of the drawbacks of long form of periodic table. Another one, lanthanides and actinides have not been accommodated in the main body. That is another problem. Lanthanides and actinides have not been accommodated in the main body. That is another problem. Okay, nomenclature of elements with atomic number greater than 100. Already we mentioned that. What is UUT, UUP, UUS? We are trying to give answer to that question. When an element is discovered, we'll give a temporary name to the element. For giving this temporary name, there are certain rules. These are the rules here. The name is derived directly from the atomic number of the element. That's the first one. The name is derived directly from atomic number of the element. And for this, we will use numerical roots. Numerical roots for numbers 0 to 9. For 0, the name is nil, N-I-L. 1, UN, un. 2, bi. 3, tri. 4, quad. 5, pent. 6, hex. 7, sept. 8, oct. 9, n. And if the element has atomic number 100, first you have to write the name of 1, UN, un. Then the name of 0, nil. And next is 0, nil, un, nil, nil. But the name should end with the IUM. Therefore, the name nil, nilium, 100, nilium, 1, nil, 0, 100, nilium. And if it is 101, anium, anium. If it is 102, nilbium, nilbium. That is the name. So, nilium, 100, nilium, 100. We will take a capital U of un. Then small n, 2 small n. UNN will be the symbol. When we give a temporary name to element with atomic number 100, the name is anilinium and the symbol is UNN. 102 anilbium and the symbol UNB. When you solve examples, you will understand it clearly. So for example, what is the name for 115? 115. 1 un. So repeating 1 1. So un. 5 pent. Unpent. The name should end with the IUM. Unpendium. So UUP. Did you understand what is UUP? UUP is unpendium. Okay, here the names from 101 to 118 are given, and if you have any doubt, you can refer this one. Now, permanent names are given to all the 118 elements. It is applicable only at the identification of the element, immediately after its discovery. Okay, now the classification on the basis of the electronic configuration as S, P, D, and F blocks. The S block element. The elements of group 1 and 2, they are known as S block elements, which have NS1 and NS2 outermost electronic configuration. The thing is very easy and you know it. They are all reactive metals with low ionization enthalpies. They are never found pure in nature. Highly reactive, therefore they will be in the combined state as compounds. Ionization energy, what is ionization energy? It is the energy required to remove outermost electron from an isolated gaseous atom. We will see it in detail in the second part of the chapter. Their compounds, with the exception of those of lithium and beryllium, are predominantly ionic. These elements, first and second group elements, form ionic compounds. Now the P block elements. P block elements comprise those belonging to group 13 to 18. Groups 13 to 18 is known as P block. S and P block elements together known as representative elements. S and P block elements together known as representative elements. You have to study that name, representative elements. S and P block elements together. The outermost electronic configuration NS2, NB126. For group 13, it is NS2, NB1, but group 18, it is NS2, NB6. So we can write the general electronic configuration as NS2, NB126. At the end of each period is a noble gas element with a closed valence shell, NS2, NB6 configuration. Noble gas, the general electronic configuration, already we mentioned it. I think it is clear to you. Two chemically important groups of nonmetals are the halogens group 17 and the chalcogens group 16. They are chemically very important groups, group 17 and 16. 17 known as halogens and 16 known as chalcogens. The non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. As we move down in a group, non-metals character changes to metalloids, then to metals. For example, we know in the case of group 13, boron, that is not a metal, but aluminum is a metal. As we move down the group, metallic character increases. And as we move from left to right, non-metallic character increases. Boron, from boron to carbon, carbon is non-metal, carbon to nitrogen, nitrogen to oxygen, oxygen to fluorine, fluorine to neon. The non-metallic character increases. But as we move down the group, metallic character increases. Now D block elements or transition elements. These are the elements of group 3 to 12 in the center of the periodic table. These are characterized by filling of inner d orbitals. Inner d orbitals. Usually we will write the electronic configuration of, for example, electronic configuration of scandium, atomic number 21. What is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. 4s2, 3d1. So outermost shell is 4. But the electron filling is in inner 3d. Inner 3d. That is given here. Filling of inner d orbital. If we take outermost shell as nth shell, electron filling is in n minus 1. If outermost shell is n, then electron filling in n minus 1 d orbital, isn't it? It is penultimate shell. And general outer electronic configuration n minus 1 d, 1 to 10, ns 0 to 2. Usually it is ns 1 or 2. ns 1 or 2. 1 or 2. Two possibilities. They are all metals, transition metals. They are also known as transition metals. From that it is very clear they are all metals. They mostly form colored ions, exhibit variable valency, some characteristic of D block. Paramagnetism, and they can be used as catalyst. Transition metals form a bridge between the chemically active metals of S block elements and the less active elements of group 13 and 14. Very active first and second group and less active 13 and 14 groups. It is a bridge between these two. Therefore, they are named as transition elements. Now the F block elements, or they are known as inner transition elements, because the F block is actually inside the D block. Therefore, the name inner transition elements. The two rows of elements at the bottom of the periodic table called the lanthanoids, cerium, atomic number 58, to lutetium, atomic number 71, they are known as lanthanoids. And thorium, atomic number 92, lawrencium, atomic number 103, they are known as actinoids, are characterized by the outer electronic configuration. What is the general outer electronic configuration of S block? N-2 F1 to 14, N-1 D0 to 1, NS2. That is general electronic configuration. You have to study all these general electronic configurations. In this case, they are all metals. They are metals. Actinoid elements are radioactive. All the actinoids are radioactive. The elements after uranium are called trans-uranium elements. They are synthetic elements. Up to uranium, they are naturally occurring, but after uranium, the elements are synthesized in the laboratory. Therefore, they are known by the name trans-uranium elements or synthetic elements. So here we mentioned three terms: metals, metalloids, and non-metals. What is meant by metal, metalloids, and non-metals? You may have a good idea about this. The metals, about out of the non-elements, 118 elements, about 78% is metal. 78% is metal. Metals are usually solids at room temperature, exception mercury. Gallium and cesium, when you take it in your hand, it will melt. Their melting points are also very low. And the metals usually have high melting and boiling points, exception we already mentioned. They are good conductors of heat and electricity. They are metals. But non-metals, solids, they can be solids, gas or gases or liquids. They are usually solids or liquids or gases at room temperature. Bromine is a liquid, a non-metal. Carbon is a solid, fluorine is a gas. And they have usually low melting and boiling points. But there are exceptions. Boron and carbon are the exception. They have high melting and boiling points. And the non-metals are pure conductors of heat and electricity. Pure conductors of heat and electricity. Most non-metallic solids are brittle and are neither malleable nor ductile. Metalloids, what is meant by metalloids? They have the characteristics of metal and non-metal, both. The elements silicon, germanium, arsenic, antimony, and tellurium are metalloids. They are actually present diagonally in the periodic table. And they have the properties of metals and non-metals. Okay, it is enough for today. We can stop it here.